Some people like to climb mountains. I like to build planes in the air.
I grew up wanting to be on a wing, wanting to be up this high.
Sometimes the temperature up at altitude will reach 60 below. It's brisk, it's refreshing.
You never know what you're going to come across up here. Canadian geese, mallards,
owls.
These people back here, that's why I come to work. That's why I build airplanes in the sky.
We're not just building a plane here. We're building a dream.
I love this job.
I do a lot of things up here. When I look over there and I see that little kid, the look in his eyes, that's all the things I need.
Yeah, well, this was a movie, I'm sorry for the quality, but this was one from the 80s. And I think it depicts CI/CD, so continuous delivery. I wanted to share that with you. So my name is Floris Sluiter. I'm an independent consultant. I'm at level 47 in the game of life. But I'm also a double bass player. And yesterday, my presentation coach, he asked me if I would be afraid to talk in front of a public. And, well, I don't expect many of you know that the third movement of the first symphony of Mahler starts with a double bass solo. So there I am, sitting in a hall 4 times the size of this one. An audience of 2,000 people turned out. The concert is sold out and packed with people. The audience, the orchestra. I sit in a group of 10 fellow bass players, all knowing exactly what is coming. And after 2 very energetic and loud movements, and I'm sweating and I'm tired, about halfway into the symphony, everything quiets down. And then softly, a timpani starts. And after a few beats, I'm seriously shitting my pants. And then I play my solo. Anyway, you didn't come for classical music, so I should be fine now talking in front of you. My topic today is an ETL tool that I developed. We called it the Elastic Big Data Box, and it allowed for massively scalable ETL in real-world applications. And we did it the hard way, and I'll show you why. So scalable. It scaled tremendously. We did 4,000 ETL jobs in an hour each day. And I kept a screenshot of when we reached 1 million. But in the end, the tool did much more than that. But those are 1 million successful completed ETL jobs. So that was a big milestone for us. The company I worked for at the time was a small startup, Human Data Associates. It was fun while it lasted. It was a proper startup, so it failed. But we did online marketing measurements, digital data analysis. So we gathered data from Google Analytics, Facebook, LinkedIn, and all the other cookie jars. But we also connected to, for instance, the fulfillment centers, the warehouses where the web shops store their goods and send them to the customers. The financial department, exchange rates. So one of our customers was a big coffee company in the Netherlands, and they had 48 web shops, 300 brand sites, and we measured that for them worldwide. Visualization was done in Tableau, and yeah, that's this slide. So what was the problem? When I started, the data pipeline needed major work. Basically, we had a big ball of mud. And I don't know if software patterns are still a thing, but software patterns in the days were standard solutions to a set of common problems. And if you start working on a piece of code written by somebody else, you notice that almost always it follows the same pattern. It's undocumented spaghetti code. So I added the link to read up what to do, and it gives you a standard solution, which is, of course, start over. Hopefully a fun read. So the requirements for the tool were secure, robust. They're all very important when you provide services to big enterprise corporations, because you will get audited, and they do not appreciate failures in the tool or in your way of operating. And many of your customers, many people depend on flawless operations, so it's very important to get this right. So I started from scratch. Well, if you have a hammer, everything becomes a screw, but we focused on a small number of well-known tools. PostgreSQL is a DBMS. Talent is the Java framework for ETL. Amazon hosted. And I'll show you the architecture, parts of the architecture that put this together. So maybe you notice it's big data, but I still used an old-fashioned technology for it. So big data, as in many cases, but in our case, it's not so unstructured and it's not so big. If you look in practice, it usually is a maximum of a few terabytes. And the queries and the analysis that people want to do is quite often a random search, many sub-selects to make specific data analysis. And actually, tools like Hadoop or the Spark and they don't allow that much for random search. And because the data is not so unstructured, it's actually quite sensible to use an SQL tried and true database. And as you will see in the talk later on, that the database also, we had two kinds. One was for the data warehouses, one was for the tool management, the management tool. And there I use a lot of in-database functions for the actual control of the data flow. And that is a bit opposed to doing it all in code and just use the database for storage of state. But it worked. We had a minimal amount of very simple SQL code in the rest of the tooling. And all other apps become much more simple if you do it that way. So that was for us a way to develop quickly. And it facilitates highly optimized queries on the data in the data warehouse and also reuse of those. Let me see. And it's maybe not bad to use a 40-year-old way of working. You benefit from 40 years of expertise in optimization. Today, I think this year, it's 40 years ago that Oracle released the first relational database. And also, if you look at, if you're selecting tools and you look at benchmarks and all the marketing talk that people put on their websites to tell you how great their tools are, the benchmarks that you read are usually a bit rigged. They're published by a competitor, and they make remarks like, we did not add indexes as we wanted to measure raw performance of the server, or my product is fast in my showcase, it runs on 20 servers, and the database that I'm comparing it with is only running on a single server. So in my view, you need, if you have benchmarks, it needs to be properly on the same hardware and done with some respect for the original tools. So why PostgreSQL? For me, PostgreSQL started in 2005. At the time, and still MySQL is the most popular open source DBMS. But in those years, I needed a few features that were interesting to me. So it was fully transactional, the SQL was standard, it had the role-based access control. It was very particular in data formats. If you try to put an integer of 16 bits into of 32 bits into a field of 16 bits, then it would fail. Many other databases just accepted that and threw away half your data. It also was good in concurrency. I worked at a different tool than this one, but I needed lots of connections to it. It had a GIS library for geographic stuff, and it was programmable. However, feature lists never compare on performance, and I found one benchmark at the time, and for me it proved that Postgres, for my use case, was at least a better one. I have to put a disclaimer here because it is old. This is 10-year-old information, so don't. I'm sure that currently some of these things that I show will be fixed. But here on the right you see the benchmark of MySQL 5 in a few different configurations. But what you see, the more concurrency you get and the more requests you do, at a certain point it fails, but it also deteriorates. It's not only that it can't do more, it starts to do less when you request more, less than what you were. And there's a lot to be learned from a graph like this, because almost every system has a breaking point like this. And if you are designing for distributed data processing, you'll hit these kinds of graphs very fast. And the trick is, of course, to stay on the top and never overload your system. So I'll give an example, I think, later on in the presentation. But this is good to keep in mind when using distributed systems. You're basically doing a DDoS attack against your own server. That actually remembers me. I consult, and for a big financial corporation in the Netherlands, I found a similar thing. They actually threw in more hardware. It was slow. Let's put in more hardware. It became even slower. And what they were doing was they were overstressing their database and having this issue. So it actually is also a very practical thing that you see. So of course, this was the Postgres 8 at the time. They're now at 11. And here you see that for this particular use case, asking for more concurrency, doing more parallel threads doesn't deteriorate. It just doesn't give more data. So it evens out, and then there's a maximum, and it's usually determined by network bandwidth or disk bandwidth, or the amount of CPU cycles that are available to your application. But this is how you actually want your application to look once put on the stress. But of course, benchmarks can be rigged. This was actually done quite by MySQL gurus. It was a big website. I put in the link before, so if you look up the presentation afterwards, then there's a link to the full story. And they wanted to evaluate if Postgres was a help there, so they made a fair comparison in this case. So the other tool that I was using was Talent. It's a Java framework. This is the marketing speak. It's actually not that fast. It's fast in development time, but not fast in execution. It is quite powerful. They have connections to many different data sources. And for us, also important, it can be compiled and packed into a standalone application and then run on fairly straightforward Linux installations. And Talent is graphical, and because our data flow is actually quite complicated, then a graphical tool helps you. The framework it uses itself is Eclipse, and many of you use that as your favorite programming tool, I expect, but this is a framework on top of that. So remember the requirements. It needs to be fast. It needs to be robust. This is the data flow that's happening. On the left, you have 40 odd data sources: Facebook, LinkedIn, the data warehouses, the fulfillment, the web shop data, and we needed to query those daily, very fast. And then out of it comes like 8 different data formats. In raw form. We stored that because we needed to have the data provenance. You wanted, if there are any issues later on with, so you report a certain amount of money, then you can always show, okay, the raw format already contained that data and it wasn't our fault. The raw format got transformed to a single internal JSON-based format, intermediate, and then from there, from that format, we had components to map it on the target platforms like databases, or sometimes also deliver it as an Excel file or such, or to Tableau. And the optimized, the target components, the format for those were of course optimized for the targets. So why do we do this? It's in this way because why not? There are plenty of tools doing Facebook data to SQL databases. So why would you go about all the very complex set in between? And it's actually because if you do 40 sources on the in and you do like 3 or 4 on the target, then it's 4 times 40, and you have to write 160 modules or small components. And here, of course, it's 40 connecting to the data sources, 40 transforming to internal, that's 80. And then that format, only 3 for the target components. Adding a new data source will actually mean that you only have to write 2 components and not the amount that of targets that you have. So it's a much more stable way and more economical way of doing this. So we designed it for distributed execution. So jobs and processes will fail, as we all know. What we did, we specifically designed to make a resume after fail easy. We created a panic button. If you run thousands of jobs at the same time, you can push the panic button and it will freeze for a while. So it will not generate more errors. It will freeze operation. And it gives you a little bit of time to figure out what's going on. In that sense, you don't have to shut everything down. You can just hit the panic button and you have a bit of time. Can I fix it in this time? Or do I have to shut down the whole system? Usually you can fix it. Usually it's just a password fail or something like that. Especially when you enter new data sets. Scaling and sizing, I showed the benchmark before, so we do loaded the system until 90%, 95% of capacity. If you do more, it will just slow it down. Also, you have to look at how much queries you send to the sources. We did have Google on the line calling us or contacting us, asking what we were doing, because we were sending so much queries to them. And the same for Amazon. If you scale up, then you have to call them and tell them, yes, I do want 50 servers at the same time running. It's not a mistake. Another thing to keep in mind is that communication overhead between processes does take time. It's significant. The more processors you have, the more communication you're going to get if they are depending on each other. So creating bottlenecks in that sense is very easy, and that will actually limit scaling more. So if you, from the start, design it that is not the case, then that makes the maximum scale higher. And I'll come back to that later, how we did that. And we made it modular. Of course, you know, that's an easy way of divide and conquer, where you put some problems in one module and some problems in another, and then they don't interfere with each other. So I'll show you some of the modules with it in Talent. As an example, most of the data sources went through an extract Google Analytics, transform it to the intermediate format, and then we added an extra step, prepare for loads, and then we load to, for instance, the database. And this is the master job. So a job will get started, one of these 4 that I just named, and the end state will be done. Then it's fine. There might have been an error, or it suggests to postpone. If you contact Google, then you get sometimes you get a return which says, okay, try later. And of course, we could. It will get postponed, for instance, for 10 minutes. And then try again. So a job can start, get a temporary failure, and then it will be retried a bit later on. This is an example of how that looks for the extract job. So you have a few components. On the top, it makes a connection, and on the end, it writes back the data on the bottom, and then push it to S3. So the design of the master job database, a little bit on the scheduling. Of course, to start and monitor and process so many jobs, we need to schedule jobs, and a bit on parallel processing. So a job is defined to operate on data, but the data is stored elsewhere. So it retrieves it first, it operates it, and then it's stored it again outside of the server. There's no local data kept. A job can be executed after its scheduled time, not before, obviously, but there's no guarantee how long after the scheduled time. So it can be immediately, but it can also be an hour later if there's a lot of work to be done. That's written in the design. And there's also no guarantee on the actual duration of the execution. So after time, it can take 2 hours or 4 seconds. The average job time was a few seconds. But we had some that were actually running quite long. And the job can be scheduled daily, hourly, weekly, once a quarter, it doesn't matter. But so when it comes up, then it will be executed. So here I show a bit of the mathematical model behind how we designed this. So a job can be blocked by only one other job, its parent or its predecessor. But a job itself can block multiple other jobs, so its children. And any job that's not blocked by time, so it's scheduled, and its predecessor finished, then it can be safely executed. And because modeling it this way, it's of course a bit obvious maybe, but you are certain that you can execute it, and you're certain that you can execute all of them that are not blocked. So if you have 50 jobs in a queue, then you can execute them all at the same time. And it makes it easy because we also didn't guarantee when it will be done, that if you start 10 servers, it will just pick the top 10 jobs, execute them, done, and then take the next ones. And if you need a faster execution, you add more servers. If you think, okay, we're almost done, doesn't matter anymore, then you terminate a few, and then that makes it cheaper, of course, in Amazon. Our tool, we tried, it scaled up to 50 worker nodes. It did 2 to 4 seconds per job, so it did on average 10 finished jobs per second on the highest thing. So I see I have 10 more minutes. So the API, very simple, get a job, how much jobs are in the queue, and once you get a job, then of course you have to report back when you're done with it. And based on templates in the database, we could generate the schedule for today or for the next month. So this is, I was asked to put some code on. I'm not sure if it's on the readable in the back, but you can look up the slides later, of course. So to get parallel execution, if you do that in code, then it's usually a lot of libraries, a lot of painstakingly stuff to get thread safe, and well, it's a nice bug hunt. It can be a nice bug hunt, but by using a database, I only added 2 words in my select statement, and it says for update. So if I do a select for update, then I'm ensured that this process is the only one getting that job ID. And then I could scale easily. So we also used the Postgres for the data warehouses. It was 1 per customer. Each had their own table. Each data set had its own table in its close to its original format. We didn't do much normalizing or other real transformations, because the data is, of course, already in its original format quite ordered. You might want to map customer ID to consumer ID or something like that, but it's in essence it's already quite good. Otherwise, you're not using the correct data. So, architecture in Amazon. On the left again, it's the environment of the company, of human data. On the right, there's 1 customer. We had quite a few, but they were all identical. Yeah, it's all in a VPC. We had to put in extra care to make it secure, and so that data wasn't leaking between customers, but also not outside, of course. It's some of the data is privacy related, others is financially valuable. So the companies didn't want their competitors to know what their revenue was for a particular website. Yeah, what else can I say? It's actually quite straightforward. I'll take questions later if people want to know more about it. Worker nodes, the actual executors of the jobs, they were in an auto-scaling group, and then an auto-scaling group is actually designed to make it resilient. So if a server terminates, then it automatically starts anew. But of course, if there are no more jobs, then we want to terminate it. And at the time, it wasn't very well documented at AWS. Last time I checked, it's better documented. But there is a trick. You can, from within your own server, you can tell the auto-scaling group, I want to get out. And then also lower the amount of servers that need to be running. So I get out, and you have to lower the number, because otherwise you get out and it will automatically start another one. And then you can safely terminate yourself. To show you how this looked like in practice for us, the GUI, all green, all good. There's a panic button, but we don't need it, it's green. There's also a button, reset the errors. If you have failures and you fix it with you bought some time with a panic button and you fixed it, then you can do reset, and hopefully you're good. Errors did occur, so we did use the panic button, just to give you full disclosure. And it scaled to up to 4,000 ETL jobs in 1 hour each day. And if we had a new customer, that could easily get to hundreds of thousands of jobs just to get all the history in. And then we needed to ramp up to many more. So, some final remarks. I think this is nice. Let's see if this works. Yeah, it's fired up.
All right, I introduced to you Leonardo, and he's going to paint a picture for you guys in the way that a CPU might do it, as a series of discrete actions performed sequentially, one after the other. In 3, 2, 1. Let me speed it up. Ladies and gentlemen,
Leonardo 2.0.
when we hit this trigger on this thing, 2,100 gallons of air goes through these accumulators, out these valves, into all 1,100 of these tubes, into these tubes in which the bottom of is a paintball. Each of those paintballs will fly across 7 feet of space and in 80 milliseconds reach its target. Hopefully, when it's all said and done, it's going to paint the Mona Lisa.
GPU painting demonstration.
Yep.
In 10,
9, 8,
7, 6, 5, 4, 3, 2, 1.
Ladies and gentlemen, science class is now over. Thank you.
Yeah, it's a little fun movie showing that parallel execution is actually a way to go if you want to handle a large workload. So some takeaways I hope you got from my talk is design for scale, make it pleasantly parallel. Beware of DDoS, denial of service attacks on your own systems and on your sources and targets. And if you throttle, if you ramp up, be aware that there is a maximum beyond which your own systems will fail. Thank you.
Thank you very much. Any questions? Yeah.
It's on
Okay.
the website maybe.
Yeah. I have another question about one of the requirements that you posted.
Yeah,
that
sure.
first was configurable. How do you manage that one? Because
Yeah, configurable. So we had 40 data sources, but for each and every customer you get different connection information. So we had a component that did the Google Analytics extraction, but we could send it a set of connection details and also which query to use, and it was all in a database. So job description was consisting of those data information. So every data source, if you have 40 data sources and you do 4,000 jobs, then of course you can do the math, and there are like 100 different similar jobs to the same source, but each with different parameters. And the parameters were stored in the master database next to the schedule. So if you do a call on the get job ID, then you could also request, give me the job details as a process.
yeah.
Yep.
Okay, thanks. Another question. Would you use the same tool if you had to build the same project again?
It's a very good question. I would use Postgres because it's a tool I know I'm very familiar with. Maybe you got that from the presentation, but it's I would use that. I not necessarily would use Talent because it is a bit finicky in the sense in data handling. It has a lot of connectors, but in the end, if you do it in something like Python, or you get also a zillion of libraries, and it actually might be a bit easier to do that. So in hindsight, I'm not sure about Talent. It's straightforward, but it's still you have to program it, and it's not always the optimal tool to do it. So I might use it differently. And at the time, we couldn't use Airflow because it just wasn't mature enough. In the past few years, it of course matured. And you get tools like Apache Niffy that look interesting. So I would revisit my idea. It's not meant as this is the state-of-the-art way of doing it. It was meant as, okay, there's an approach. If you're careful, you can really design for scale. That's the takeaway what I wanted to offer you guys.
Any other question? Okay, thank you very much.
Yeah, thank you.
For him.
Enjoy.